Everyone, so welcome to part 2 of my MR lecture series. Today I'm going to be talking about pulse sequences, signal-to-noise ratio, and safety in MR. So I've got the three images here to kind of illustrate that. First I just want to recap from my last talk, because I was talking about how we fill K-space. We send in a 90-degree pulse, use the slice select gradient just to image a slice in the patient's torso, for example. And then we can apply a 180-degree pulse, or not. I'll go into different pulse sequences today. And then we apply a phase encode gradient and a readout gradient just to localize the signals. So just to fill out one line of K-space, and then we wait time TR, and we go back, we do the same thing, and we basically just switch on another phase encode gradient and read that out. So that's basically how we fill out K-space. And what's happening with the signal over time is that we give a 90-degree pulse, and then the signal starts to decay, and then there's a little bit of regrowth after the 180 pulse here, and then we start to sample at around time TE. And then that's basically what we're measuring in the readout gradient. And then in terms of K-space in the center here, it's the lowest amplitude, and it will give us a measure of contrast, and then at the edges it'll define the higher frequency, so define edges and stuff. So that's basically where I left off from the last talk. So the first thing I'm going to talk about is pulse sequences. Basically it's a timeline of how MR signal is generated. These are like diagrams with series of lines, as you'll see, and the type of pulse sequence that is used will affect the image contrast, the resolution, and even artifacts because of the speed. And artifacts is not something that I'm going to talk about in this talk. I'm going to leave it for either part 3 or part 4, but I'll definitely get to those. So this is an example of a pulse sequence diagram. This is a spin echo. So in a typical spin echo, what you're going to have is a 90-degree pulse and a 180-degree pulse. Now this is just like a very simple example of how you would fill one line of K-space using a spin echo pulse sequence. So first you would send in a 90-degree pulse and do a slice selection at the same time, and then you would turn on the read and phase encode gradient for localization, and then you would do a 180 pulse with a slice selection again, and then you would wait and then read it out near time TE. So then you would wait TR, and then you would go back again. And you would do use another phase encode gradient with a different amplitude. So basically what's happening over time is what I had explained before. So basically you're watching the signal decay after you apply a 90-degree pulse, and then you apply a 180 pulse and you watch the signal grow, and then you start to sample at around time TE. So this is an example of filling out in this case 2 lines of K-space if you go back and do it again. But here's an example of a multislice sequence. So in this case I have the same sequence set up here, and we don't want to wait. TR is quite a long time, and we don't want to wait TR, which is on the order of seconds, to read out one line of K-space and then go back, because you have to read out many lines for many images. And TE is actually much shorter than TR. I've put 1/10 of TR here, but it might be shorter than that. There's no rule of thumb, but just as an example. So what you can do during that time is actually, so you would read out one line of K-space here, and then you would wait, and then you would just start to acquire the first line of K-space in the next slice. So that's what I'm showing down here. So you'll read out the first line of K-space for image 1 and image TR, and then you would go back and you would turn on the phase encode gradient, use a different amplitude, and read out the next line of K-space. And then you would just keep doing this over and over again. And this would really save on time because now you're not waiting TR just to acquire one line of K-space. You're waiting TR to acquire multiple lines of K-space within different images. The exam time is equal to the number of phase encode gradients times TR. That's for a single slice. And if you want to know the entire exam time, you would take this product here and multiply it by next. So next is like the number of times the K-space is read out. So sometimes it's equal to 1, 2, I've seen 4, but this entire product here will give you the exam time, the total exam time. And if you wanted to add a slice, an extra MR slice to your scan, you would have to increase the TR. But just remember that lengthening the TR will change the contrast in each of these images. So that's something to keep in mind. I don't want to go into this too much, but when I start to talk about signal to noise ratio, this will make a difference. So it's this the fact that the RF pulse that you send in is not a perfect square. And so sometimes when you're imaging different slices, you might excite protons in slices that are overlapping with the next one. So what you're going to get in your reconstruction is crosstalk or overlap. We call this interleaving. So I don't want to go into that too much, but I'll show you later how that affects the SNR. This is a Multiecho spin echo. So this is like a modification of the spin echo, and this one is pretty cool because you do a 90-degree pulse, you have a slice selection, and then you do a 180 pulse for slice 1, and then another one for slice 2, and basically what you're doing is just reading out these different lines of K-space. And what's happening, and this is something that you should be aware of, is that what you're doing is basically exciting, you're applying that you're applying the 90-degree pulse. You're watching the signal decay. So you're watching these protons go out of phase with each other. Then you're applying a 180 pulse and watching that signal grow and then decay again. And you're sampling during that time. So time TE, this is where you're sampling. And then again, you're applying, and then as you let the signal phase out, you're applying another 180-degree pulse here and watching the signal grow again. And then you're also sampling at time 2 TE. So you're going to have these different slices. And then when you come back to the beginning, again, you're just going to change the amplitude of the phase encode gradient, and you're going to read out another line of K-space. So you're going to essentially end up with these two slices. So these are I should mention that these are the same image like this, but they're just different contrasts. So and this is something that I've typically seen during an ACR accreditation image acquisition. Sometimes you'll get a proton density image with a T2 image, which basically they have different TEs. So for slice 1, I'm going to have TEs equal to 20, and then for slice 2, I'm going to have TEs equal to 280. It's the same image though, it's just they have different contrasts. The last one is a gradient echo. So basically, in a gradient echo, you'll see that there's no 180-degree pulse here. So you have a 90-degree pulse, then a slice selection, and then basically you're going to watch the protons decay, phase out, go out of phase with each other. Sorry. And then you're going to apply a phase encode gradient and also a frequency encode gradient, but one thing you're going to do is accelerate the dephasing, and then you're going to refocus or rephase these protons to come back to give you a signal that you're going to measure. So that's how the gradient echo works. You don't need a 180-degree pulse. Now, what are the different? Oh, and of course you'd have to come back again and apply the another phase encode gradient just to read out every line of k-space. So what is the difference between a gradient echo and a spin echo? Well, for gradient echo, there's no 180 pulse, as you've seen. As for speed, it's relatively faster than the spin echo. There's a shorter TR, which is good for contrast. The flip angle, so the flip angle doesn't need to be 90 degrees. And this is something that I won't go too much into, but just so you know, there's this thing called the Ernst angle. And this is empirically measured. So this graph is showing the signal intensity versus the flip angle. And these are materials A and B. So different materials have different optimal flip angles. And by optimal, I think I mean the difference in signal between the two materials that you're interested in looking at. So if I were to, use a flip angle of 10, like over here, I wouldn't get a significant signal difference between A and B. They would pretty much look the same in the image. But if I was to use a signal difference of, somewhere between 75 degrees and 80, I would get a pretty good contrast between material A and material B. So the Ernst angle is actually related to TR and T1, as you can see from this equation here. So I won't go too much into it, but just so you know it exists, and it does affect the SNR, as I will show you later on. Another example of a pulse sequence is called inversion recovery. This one's actually my favorite because it suppresses material that you don't want to look at, and I find that useful. As you can see, like looking at this part here, this looks like the spin echo sequence. The only thing that I've changed is the initial 180-degree pulse. So let me just show you what the method is here. So in inversion recovery, basically you're going to flip the protons 180 degrees, and then you're going to watch them grow. You're going to watch the net magnetization grow. And for different materials like fat, muscle, and CSF, for example, they're going to grow at different rates. Now, if you try to apply a 90-degree pulse to get a signal, for muscle and fat here, you won't see a big difference between the two signals, and maybe you want to see a good difference between fat and muscle. If you apply a 90-degree pulse here, you might see a good difference between the two, but it just seems like you're just randomly applying a 90-degree pulse. If we strategically place this 90-degree pulse at a certain point, we can completely cancel out fat. So while the protons are growing in the longitudinal direction, basically it gets to the point where fat will have no transverse magnetization, and so we won't get any signal from fat, or very, very little. And this is at time Ti. So if we apply a 90 degrees pulse here for all these different substances within the image, basically we're going to cancel out fat. And this the name of this inversion recovery is called STIR, so short TI inversion recovery. It's a fat suppressed image, so the TI is quite short. There's also FLAIR, which is the fluid attenuation inversion recovery, and basically you're just trying to cancel out the CSF. So this is mainly used in the brain, so CSF is in the brain. So SNR. So that's enough for pulse sequences. Now we're going to switch over to signal to noise ratio. So noise is basically, there's a lot of things that contribute to noise, electronics, the physiology. It's something that you're constantly balancing signal against, especially for MR. You have like a constant noise in the image, And so what you want to do is like basically try to, modulate the SNR, changing the amount of signal in the image. And where does the MR signal come from? Well, it comes from the hydrogen nuclei that's attached to the water in the tissue. Each hydrogen proton has a unit of nuclear magnetism. So the greater the units of magnetism, the greater the magnetization turned into MR signal. Therefore, it's the number of protons that we have for that signal. So imaging a fixed volume of protons will directly translate into the number of protons in a voxel. And the density of the tissue doesn't change, but we can change the voxel size. So selecting your parameters for imaging patients will affect the SNR. And the spatial resolution is a direct determinant of SNR because, if you decrease the size of your voxels, you're changing the number of protons in your image. Therefore, you're changing your SNR. You'll have worse SNR with smaller voxels. So, as I've mentioned. And I've put an equation here. SNR is equal to the voxel volume square root of ny, which is the number of phase encodes, the number of times you average the frequency encoding, nex, which is the number of times the k-space is read out, over the bandwidth. So I'll go through how each one of these affects the SNR. So the first big thing is resolution, as I mentioned. So increasing the matrix size will reduce SNR. It'll reduce the voxel size and then therefore reduce the amount of signal received by individual pixels. So decreasing the matrix size will reduce the spatial resolution and produce blurry images, and you can see that here. So if the matrix size is small, you'll have higher SNR, but you also have low spatial resolution. And then, of course, if you increase the matrix size, here, you'll have high spatial resolution. Like, I can see a lot of details in there, a little bit better than this one, but your SNR will be lower. Now, looking at these images, I mean, I'm not a radiologist, but I think all of these images look good, but it depends on what they're looking for. So certain protocols may call for higher spatial resolution. So if that's what they need, then use that. Also, slice thickness will affect the SNR, and that's because it has to do with the volume that you're basically defining, the number of protons within that volume. So if you make your slices thicker, you're going to have better SNR. So in this image here, the slice thickness is 2 millimeters, for example, and this image looks pretty grainy, but the edges are much sharper. It's better resolution. But in this image over here on the right, the slice thickness is 6 millimeters, and it's just a much more clear image. It's less grainy, and as I mentioned, it's all a function of the volume of the voxel. The field of view will affect the SNR. So increasing the field of view will increase the SNR. It'll increase the pixel size, which will increase the number of signals received by individual pixels. It'll reduce the spatial resolution and blur images. So large pixels will receive more signal and produce high SNR. So here, basically, I'm comparing the field of view between these two images here, the left and the middle one. So if you increase the field of view, you'll have very high, SNR compared to the lower field of view. And then if you're comparing these two images, the middle one and the right one, basically what I've changed here is the matrix size. So if you increase the matrix size, you'll have a little bit poorer SNR compared to the middle one. So sometimes you have to go with like different trade-offs, and I mean, I think all these images look really good. I think you can see more for the one on the right, but that's just my personal opinion. It's whatever the radiologist wants to see in the image, right? So and then next, which I sort of explained, is just the number of averages that you take. And this is, I mean, it makes sense. Like if you are once versus 4 times, and you're averaging this 4 times, then you're going to have a much better image compared to just doing it once. Also, as a rule of thumb, if you double nex, the number of excitations, you'll increase the SNR by 140%, but it also doubles the scan time, so that's something you have to be aware of. MR scans can be quite long. So I've sort of talked about like SNR, but there's other parameters, SNR in terms of like how the voxel size will affect it, but there's other parameters that will affect the signal difference and sort of affect the SNR as well, because contrast, like the signal difference does relate to SNR. So this is something I briefly went over, was the slice gap, so that interleaving. So if you have 0% interslice gap, then you're going to have a lower SNR, as you can see here, compared to like a 50% interslice gap. This shows like this is when there's some overlapping in the image, and you can kind of see that in this area here versus that. So, it does give you a higher SNR, but it also means that you're kind of averaging images together a lot more than what you would be for a 0% interslice gap. Then of course you have interleaving, which in this case doesn't look too different from this. Although no, that's not true. I guess you can see like there's some changes between these images if you look really closely. So anyways, yeah, the slice gap does affect the SNR, does affect the signal difference. And then there's a TR, of course. We know that increasing TR will increase the SNR, as high TR will allow the longitudinal magnetization to approach its max and produce high signal intensities. Beyond a certain limit, it will reduce the T1 effect, though, and that's something to keep in mind. So if we go down here and look at the image on the left, we have a TR of 200. It's a pretty low SNR, because it's not very long. But compared to a TR of 500, I mean, this image looks a lot better than this one. You have a high SNR, and you have a high tissue contrast. But if you let the TR go for too long, if you remember, like those curves eventually, like they kind of come together for different tissues. So you're going to have low tissue contrast, but you might have high SNR. SNR is basically the signal difference, the signal that you want to measure versus the background. So you can still have high SNR, but very poor contrast, which is, what we see here. So this image here will lose that T1 effect. So this image here looks the best out of all three, clearly. And also TE, so this is something that's selected by the tech. So TR and TE, if you recall, are selected by the tech. So if you increase TE, that will reduce the SNR. And decreasing TE beyond a certain limit will reduce the T2 effect. So, I mean, in this case, I'm showing good SNR for both and like high tissue contrast, but you can see if you kind of play around with the TE, you can get kind of different looking images. So it's whatever the radiologist wants to see. That's usually my answer. It's like, what is the radiologist looking for in these images? And of course, I sort of mentioned the flip angle that will affect the contrast. So a flip angle of 120 in this case seems to fare a little bit better than a flip angle of 50. You can see the differences in the SNR quite clearly. So, although, in my opinion, again, like flip angle doesn't look like it has a huge effect on the image. Depends on what you're looking for again. So, it's always just something to keep in mind. Lastly, I just want to go over safety. So the American College of Radiology has defined 4 safety zones within the MR facilities. These are denoted zones 1 through 4 in Roman numerals, and they correspond to the levels of increasing magnetic field exposure, and hence the potential for safety concerns. So the schematic here shows, like, this is zone 1 out here, and then this is zone 2, which is, the reception area, Zone 1 is like the public area. Zone 2 is reception, and where the patient gets all has to remove everything from their pockets. And Zone 3 is the control room. Basically, this is like where the techs sit when they're scanning patients. And then Zone 4 is the magnet. So if we go over each zone again, so this Zone 1 is freely accessible to the general public. That's no supervision is needed there. The magnetic fringe fields in this area are less than 5 Gauss, so less than 0.5 millitesla. Zone 2 is still a public area, but it's like the interface between the unregulated Zone 1 and the strictly controlled Zones 3 and 4. So MR safety screenings typically occur here under the technologist's supervision. And then Zone 3, again, is the area near the magnet room where the fringe, gradient, or RF magnetic fields are sufficiently strong to present a physical hazard to unscreened patients or personnel. And then Zone 4 is synonymous with the MR magnet room itself, and it has the highest field and the greatest risk, and from which all ferromagnetic objects must be excluded. So don't walk in there with your cell phone, it'll erase your credit card. Something to keep in mind is the most important hazard, 90% of the time for MR, is burning tissue. Direct tissue heating leads to burns. So the FDA has issued a specific absorption ratio. Basically, it's a parameter of heating. It will establish an allowable RF energy deposition. The units are in watts per kilogram. So the SAR limit, as they put it for the whole body, is 4 watts per kilogram in 15 minutes. For the head, it's 3 watts per kilogram in 10 minutes. For any gram of tissue in the head or torso, it's 8 watts per kilogram. And then for extremities, because they're much smaller, it's 12 watts per kilogram in 5 minutes. These are just some of the FDA posters that they have on their website with regards to MR safety and labeling. These are the types of burns you get. So usually we don't put patients in with anesthesia, because if they start to burn, they won't be able to tell us, warn us that that's actually happening while they're being scanned. So there's a little bit of a ferromagnetic marker put on this patient, and that's why well, not ferromagnetic, but like lead, and that's what they started burning. So it's important, to keep the patient awake. And also, this was something that could have been tragic. There was a patient on this before they took the patient off, though, before this actually rammed into the scanner. But obviously there was some ferromagnetic material, and the scanner was pretty strong, was able to pull it in. But if the patient had been on this stretcher, it could have been fatal. So anyways, thank you for listening to my talk. Feel free to subscribe to my channel. Thank you for subscribing, and we'll see you next time.